Hey everyone, so today we're going to take a fresh look at a piece of math that is so famous it's practically a celebrity, the Pythagorean Theorem. But as we're about to see, behind that simple little formula is this incredible story of ancient surveyors, brilliant proofs, and believe it or not, a deep connection to our modern world. All right, let's get into it. Just for a second, think back. If you had to pull just one mathematical equation out of your memory from all those years in school, what would it be? Yeah, for most of us, there's a pretty clear winner.
Yep, there it is. A squared plus B squared equals C squared. So simple, so elegant, and it's been a cornerstone of mathematics for, well, millennia.
And this right here is the classic way to picture it, right? The image we all saw in our textbooks. The idea is that if you've got a right-angled triangle, the area of the squares you could build on the two shorter sides, that's A and B, add up perfectly to equal the area of that big square on the longest side, the hypotenuse, C. Seems pretty straightforward. But what if I told you that the real history of this theorem and what it's truly capable of is way more surprising than anything we learned in geometry class? So first, let's pull this theorem right out of the textbook and see how it actually gets used in the real world. Okay, so just as a quick reset, here are the key players. You've got your right triangle, meaning it has one perfect 90-degree corner. The two sides that actually form that corner, those are the legs, A and B. And the side across from it, which is always the longest one, that's our hypotenuse, C. Now this leads to a really clever practical tool called a Pythagorean triple. These are sets of three nice, clean, whole numbers, like 3, 4, and 5, that fit the formula perfectly. Builders and carpenters use this trick all the time. They call it the 3-4-5 rule. If you measure 3 units down a wall, 4 units out on the floor, and the diagonal between those 2 points is exactly 5 units, boom. You know for a fact you have a perfect square 90-degree angle. It's a fundamental trick of the trade. And that whole practical side of things, it's not new at all. In fact, that's the whole reason the theorem was discovered in the first place. And it happened much, much earlier than you might think. So check this out, because this timeline kind of changes the whole story. We all call it the Pythagorean Theorem, after the Greek mathematician Pythagoras, who was born around 570 BCE. But look at this. Ancient clay tablets show that the Babylonians were already using these exact principles around 1900 BCE. That's more than 1,000 years before Pythagoras was even born. And on the other side of the world, ancient Chinese texts described the same concept, calling it the Gogu rule. So why were all these different ancient cultures so obsessed with right triangles? Well, Dr. Daniel Mansfield explains it perfectly. This math started showing up right around the time that land was becoming private property. I mean, if you want to avoid arguments with your neighbors, you need a way to draw fair, accurate boundaries. This theorem wasn't just some abstract idea. It was a critical tool for a changing society. And this ancient Chinese diagram here shows the very same idea. It's just an amazing example of how different civilizations, when they were faced with the exact same practical problem, how do we make a perfect corner, they independently discovered the same beautiful mathematical solution. Okay, so we know that it works, and we have a good idea of when people started using it. But the part that's truly magical, the part that's fascinated mathematicians for centuries, is why it works. The logic is just so elegant. And what's so cool is that you don't need a bunch of complicated algebra to prove it. You can literally just see it. So on the left, we've got a big square, and we've arranged 4 identical right triangles in the corners. See that empty space in the middle? That's a tilted square with an area of C squared. Now look to the right. All we've done is rearrange those exact same 4 triangles. Now here's the kicker. Since the big outer square is the same size in both pictures, and the 4 triangles are the same, well, that means the leftover empty space has to be equal too, right? On the left, that space is C squared, and on the right, it's A squared plus B squared. So A squared plus B squared must equal C squared. It's just a brilliant little visual puzzle. And that's just one proof out of more than 400 that we know of. This one here, which uses a trapezoid, was actually discovered in 1876 by a U.S. congressman who was a bit of a math nerd. His name was James Garfield, and just 5 years later, he became the 20th president of the United States. How cool is that? So we've gone from ancient land disputes to a future president's hobby. This theorem has had quite a life, but its story is far from over. Right now, as we speak, it's quietly powering the technology all around us. The very device you're watching this on is using it. GPS satellites are constantly triangulating your position using its principles. When you play a video game or watch a movie with CGI, artists are using it constantly to calculate distances and render realistic 3D spaces. And for physicists and engineers, it's totally fundamental for, well, everything from calculating forces to designing stable buildings. The theorem even has a famous cousin over in trigonometry. Sine squared plus cosine squared equals 1. It's the exact same relationship, just translated from the sides of a triangle into the world of angles and waves. And that identity is absolutely critical for calculus and for describing anything that moves in waves, like sound or electricity. So, we've gone from ancient fields to modern phones, but there is one last step to take on this journey, and it's a bit of a mind bender. What happens when we push this simple little formula into higher dimensions?
First, let's just reimagine the theorem in a slightly new way. Look at that hypotenuse, C. You can think of the two legs, A and B, as being its shadows if you were to cast a light from above and from the side. They're projections onto the x and y axes. The theorem tells us that the square of the length of the real object is equal to the sum of the squares of the lengths of its shadows.
Okay, you with me? Now let's make the leap. If we use that exact same shadow idea, but in 3 dimensions, the theorem still works. It just generalizes. But now it's not about the length of a line anymore. It's about the area of a flat shape that's floating in space. The rule becomes the square of that shape's true area is equal to the sum of the squares of the areas of its shadows on the 3 different planes. So the core idea stays exactly the same. It just climbs up a dimension. In 2D, the square of a length is the sum of the squares of its shadow lengths. In 3D, the square of an area is the sum of the squares of its shadow areas. And this pattern, it just keeps on going into higher dimensions that we can't even picture. It's just a powerful reminder that sometimes the simplest ideas we learn in school, like a squared plus b squared equals c squared, are actually just little doorways to a much deeper, much more beautiful understanding of how the universe works. Thanks so much for watching.